Great, welcome everyone. So before I start, two disclaimers. This talk is 100% AI free, so there won't be any AI. And it will contain traces of functional programming, so if you're allergic to functional programming, beware. So what are first principles? And I'm going to talk about that, not the architecture per se, because we all know what architecture is. So who's familiar with the concept of first principles? One person, this is awesome. This means that you will learn something today from me. So first principles are basic, fundamental truths or assumptions about something, and they cannot be deducted from other facts about the system. So in mathematics, this would be close to axioms. Here we apply this thinking, fundamental thinking, to systems we are building. So we are breaking complex system down to its basic components, and we are able to see the gist of systems we are building, and then we can reason about fundamental building blocks. We can be innovative, we can be creative by combining these blocks, and we can actually make our decisions based on the fundamental truths instead of always using the same architecture. So today I'm going to try, hopefully successfully, to apply first principles reasoning to software architecture, to examine various architectural styles and patterns, identify common parts, extract them, and then recompose them into something new and hopefully good for you. So here I single out some of most popular architectural styles, starting with something we all learned as junior developers, which is layered entire architecture, microservices, etc., etc. So how many of you find layered entire architecture your favorite programming style? Couple of hands? Well, here is how it looks like. Entire architecture. So the yellow arrow is the flow of the execution. It comes to the API layer. Then you have services layer, domain layer. You save it to the database and respond back. This is how it started. So over time, we learned that things that change together should be kept together. This evolved into vertical slices architecture. This is well known. So a couple of hands raised when I asked who's using this, whose favorite architecture this is. And the thing is, we should be making informed decisions. So this is from the book by Mark Richards and Neil Ford, very good book about the architecture. And what you can see here is the actual attempt to grade various architectures on specific criteria. So let's look at the layered architecture. You will see that it has 5-star for cost, which means that it's cheap, and it's simple. So in a situation where we are working with a team of junior developers, we need to build something simple and cheap. This will be the right choice. So conclusion here is that there's no good and bad architecture. There's appropriate choice, less appropriate choice, more appropriate choice. Hopefully this is how we make decisions. Okay, so let's start analyzing this layered entire architecture. There's no gravity in software architecture, so we can lay it out horizontally, and we can follow the workflow. So what I did, I straightened out this yellow arrow that was U-shaped like, so you can see from the left to the right, this same set of steps that we are taking. And of course, this is so-called database-centric architecture. Now you can visually see why it's called database-centric architecture. Of course, over the course of past 20 years, I think, since domain-driven design thing became a thing, we developed some best practices or recommended architectures. So today, when you read about this architecture, either hexagonal or ports and adapters, clean or onion architecture, or functional core and imperative shell, black line represents the order of the execution flow, and what you can see, what is common for all of these architectures, domain is in the middle, domain is in the center. So first principles thinking, let's extract what is common for all these infrastructure, for all these architectures. So we're coming with domain centricity as the first principle in architecture in this talk. And again, when we go back and look from that perspective, you can see again what is common for all these architectures is that you have business logic in the center, at the core, and you have I/O at the edges. This is common characteristics. All these three architectures are coming with different motivations, but this is what is common for them. Is this a good thing? Well, I think it's a good thing because you're getting lots of things for free. So you remember this mantra, composition over inheritance. When you look at this, you can see here composition, the structure of your application. So first, you have I/O at the entrance. You're loading data either from database or some kind of input. You process it, you save it to the database. So you can see the natural flow of the execution. This imperative shell functional core can be mapped here to the imperative shell outer parts and the functional core, hopefully purely functional core in the middle. And when you think about it, deterministic business logic can be extracted, and you have non-deterministic I/O, which you cannot reason properly about. Then, going further, do you now need async within your business core? No. I/O is on the edges, and so you can go with completely synchronous code for the business logic. Exceptions are errors we cannot handle, and hopefully now we can build business logic with domain errors models as a part of domain, and we have exceptions on the edges because if database is not available, of course, you cannot handle that, you will have exceptions. This structure is easy to test because you can mock input and output and actually test the workflow in the middle. And when you look at the unit test and the integration test, you can see here that they are naturally mapping to the business core unit test and the integration test, which are integrating business logic and the outer I/O. I mentioned pure functions, and this is now we are entering a part where I'm speaking a bit about principles of functional programming. So pure functions are functions which are deterministic and that they do not have side effects. So what is determinism? It's a property of a function. Every time we call a function with the same set of arguments, we will get back same output every single time. So it's predictability, and of course you can already reason it's very easy to test. Side effects is any kind of interaction with the environment, either reading or writing. So once you start using pure functions, you can see that they have referential transparency. So every time you want to call a function, you can replace function call with the result of the execution of the function. And this, you already thinking, okay, this is good for caching purposes. Also, these are so-called honest functions because when you look at the signature of the function, complete input is expressed in the input parameters. There's no, within the code of the function, there's no interaction with the database. So everything function depends on is contained in the input parameters. So this is so-called honest function. You can test easier. You need lower cognitive load to comprehend what it's doing. When you look at the signature, it's already visible there. And these functions can be easier to compose than standard way of doing things. And also, this reuse we are all preaching about is now easier. And of course, the big topic for the future and the present, parallelization is easier with these functions because they are thread safe. So I'm extracting here pure functional core as second first principle. Of course, it's not always possible to structure your code or your workflow so that you have I/O on the edges and the pure business logic in the middle. If you need, for example, to start executing a workflow, visit something in the database to check the status, make decisions based on that, okay, you can still extract pure business logic and make it composable with the rest of your logic. And of course, there's no silver bullet. So this approach is not working too perfectly with heavy ORMs, where you mix logic that works with the database and you mix logic that is database free. Sometimes you can refactor it, sometimes you cannot. It's not take it or leave it principle. If you can convert certain part of your code into pure functions, you will benefit from that. And then, if we go back to this structure, of course, input that comes either from the database or from the users is not something we can trust. So, you have natural place for placing validations in your application. This would be this seam between I/O and the business logic. This is so-called validation on the edge. And once we perform validation, once we parse values, we have a guarantee. And in domain-driven design, those are famous value objects, but actually it's common sense, it's strong appropriate typing. So once we parse values, if we manage to parse them, we can be sure that these are valid values. So there's also a famous paper that says parse, don't validate, or blog post, I think. So I would extract semantic typing as first principle. When I say semantic typing, rich typing, don't attempt not to use primitive types. Instead of string, model first name or whatever you need to model, and build in validation criteria within your semantic typing variables. And now, zooming inside of the central box with business logic, I can abstract this to one function. I'm calling it update. This function will receive current state of the system. It will receive the command I want to execute against the system. It will execute command against the system using some business logic, and it will return new state. Of course, commands can be rejected for various reasons. It's invalid command, or you don't have authorization to execute it. So I'm returning either new state or returning the error. And of course, new state I produce is the input, again, for the next command that will arrive to the system. And of course, in the beginning, it's like deterministic automata. I need initial state. And this means that this system can be abstracted into two functions. One of them is init function, which is returning initial state. The second one is the update function, which is receiving current state and the command we want to execute, and returning either error or new state of the system, which will be input for the next command that we want to execute. And speaking of n-tier layered architecture, as a simple solution, I will also speak about transaction script design pattern. This is probably simplest pattern, where we are literally, you remember when you specify by words what you want to achieve. When you translate this human language specification into the code, you have top to bottom linear flow of the execution. That would be simplest possible programming pattern, something we'll learn when we start learning programming. And this is simple, and you can write it fast, but of course this is limited in scalability, lots of code duplication, so this is simple and cheap, but it's not suitable for big projects. But it turns out that now I can start expressing these patterns through my first principles. So at the bottom of the screen, you can see specification, abstract specification for the key value store with load and save operations. So this is load by ID and save, returning ID. And my handle function is handling command. And rather simply, even though this is functional programming and may look complicated, it's rather simple. So I will load state from the database if it exists. If it doesn't exist, I will use object.init function. Once I have a state, I will try to call my update function, process the state and command, and I will either get new state, which I will save to the database, or I will get back an error. On the opposite end of complexity scale is event sourcing. I don't know how many of you are using event sourcing, more than transaction script. So it's a principle where we are not storing the state, we are storing the events, we are not throwing away any information, and then we are computing the state from the events. Now, if we try to abstract event sourcing, it would start again with function, and this time I'm calling it decide. It will receive command and state, and instead of new state, it will return events. So we are accepting command as an intention to do something, some intervention or some state change, and we are producing events which are, as a rule, formulated in past tense. And again, if command cannot be executed, I'm returning here error. And then produced events are fed into second function called evolve. So this function is receiving current state, and the events produced from command. And then based on the current state and on the event, I'm producing a new state. So now I have decide function, which is deciding what events will be produced from the input command. I'm having evolve function, which is evolving the state, old state, based on the events into the new state. And of course, again, I have init function, which is producing initial state. And now, again, if I use these three functions and the model of the event store with load events and depend events, I can express in this abstract way event sourcing. And again, same principle. I want to get state first. So I will either load it from the database. I will use something called left fold to apply all the events since the beginning of time for this aggregate or entity, whatever you want to call it. I will produce current state of the system, and then I will take the state and call decide function to produce current state of the system, to produce new set of events, which then will be saved to the database. So again, we are having this loop which is being repeated for every function. So in the first approach, I had update and init, and in the second approach, so first approach was transaction script. The second approach is event sourcing. You see transaction script as probably the simplest pattern, and event sourcing is probably one of the most complex pattern, at least for most of the people, not used for to think in that way. Well, you can already see similarities, and good news here is that we can unify them because update function from transaction script pattern can be expressed through decide and involve functions. So this means that I'm now able to use same three functions, decide, evolve, and init, to implement transaction script. And now looking side by side, what I managed to do, I managed to extract three functions, and these three functions at the top can be used to implement either event sourcing or the transaction script. And it turns out I can use these three functions, which I'm not going to showcase today, to implement most of other architectural styles and patterns like actor model or whatever you might remember as your favorite pattern. So this is interesting because what this means now is I can encapsulate my business logic in these three functions, and I can separate them from the architecture. So this means that if I want to start quick and dirty MVP prototype, I can encapsulate my business logic into decide and evolve functions. I can plug it into this function for transaction script, release it, test my idea. If my idea is good, if I need to evolve, if I need to refactor, I don't have hard connection between my business logic and the architecture anymore. If I need to refactor my architecture into, let's say, event sourcing, I can take these three functions without changing and plug them into a different engine that will be running these two. What about the side effects? They are inevitable. Side effects meaning, going back to the definition of the side effect, they are reading from the database, writing to the database, reading from the screen. You cannot avoid them. Without side effects, our software would be almost unusable. So let's be civilized. Let's again use strong typing, strong modeling. Let's model our effects. Let's model our side effects properly. Lately, there have been some languages like Unison, which are explicitly modeling side effects. This is so-called algebraic effects. And it's not so complex that it may sound to you. It's just a proper way of modeling all these interactions which are happening with the system. If you're using Haskell, these would be things that are familiar to you. I don't know if anyone here is using Haskell. So what is the proper modeling of side effects? Well, actually, we are encoding intention here. So I want to send email from my function. I won't call email server to send. I will actually create command or side effect, which is expressing my intention. And then I will develop perform function, which will accept effect, and it will create the command. And If I go and expand my initial set of decide and involve, I now have third function, which is called perform, which will process these side effects. I know this is a bit too much, but this is the most complex slide today. Don't be worried. And you may ask yourself, okay, now for 20 minutes we've been talking about abstract concepts, how this connects to real life. Well, actually, I don't know if anyone heard of event modeling. Great. So event modeling is something crafted by Adam Dimitruk in 2018. It's just a final step in a long evolution of this methodology. You probably heard about event storming. Well, this is evolution of event storming. And what you can see here is small specification of not so trivial system. And when you look what is happening at the very top, you have forms on the screen. On these forms, users are triggering some commands to be executed. So blue ones are commands that user wants to execute against our system. We will apply this decide function, which will decide if we are allowing this this command to be executed. If we allow, as a result, we will produce event. This is the orange sticky note. And then we will use these events to produce current state of the system. And current state of the system is green stick. So these decide and involve functions that sounded rather abstract to you, you have them here. Decide function is the arrow between the blue and the orange. So from command producing events. Evolve function is the arrow between the orange and the green one. So what is also interesting is when you start applying domain-driven design, usually people are having problems with defining bounded context. Well, it turns out that these horizontal swimming lanes are actually good candidates for first version of your bounded context. So everything plays nice, and this is almost full specification. You don't need Jira tickets. All members of your team can pick up behavior of the system based on this. And now if we apply this reasoning and we start recognizing various programming models, you can see that almost everything can be encoded through command, event, and state. What you can see here are 9 patterns developed by Yves Hulleven in 2023. And I was looking at this, I concluded when I was starting, I was going to the edges, I was avoiding events, and I could almost say when I advanced as a developer, I started going into this cross. So these vertical and horizontal line where events are contained. This was real discovery for me, and this has given me hope that in the future we will be able to all become better developers. So finally, 3 first principles I extracted today are domain centricity, pure functional core of your application, and semantic typing. And I'm leaving you with these 4 powerful functions to wonder what could be done with them in your lives. I hope you will find some inspiration in this as I did. Thank you.